Welcome to AmeenAcademy.com, an engineering mechanics regarding motion of your rolling wheel without slipping. Consider a wheel rolling along a straight path in such a way that there is no slipping of the wheel on its path. Consider the center of the wheel O moves with same linear velocity how the wheel is moving. And each particle on the periphery, suppose each particle on the periphery, particularly here point P, periphery of the wheel rotates with some angular velocity, while wheel rotating, the point P also rotate as well as it translate. The wheel rotates with some angular velocity, thus the motion of any particle on the periphery of the wheel is combination of the linear and angular velocity as shown in the figure. That means the point P rotation and as well as translation. Let V equal linear velocity of the center of the wheel. Omega is angular velocity of the wheel r equal radius of the wheel. Now consider any point P on the periphery of the wheel making an angle theta with the point P and line joining the center of the wheel to the point P making an angle theta to the perpendicular OB, vertical OB. Then the particle P is subjected to the following two motions. The particle P subjected to two motions. First one, linear velocity V acting horizontal direction, and second one, tangential velocity that is V equal to omega r acting right angle to OP. Right angle to OP. Now from the geometry of the figure, in triangle OPA, geometry of the figure, we know that the angle between these two velocities is equal. Here this angle between two velocities are equal. That to theta. The resultant of these velocities r will act along the bisector of the angle. The resultant of that V and here V acting bisector of that angle theta. Therefore from this we can say r equal to V cos theta by 2. Angular velocity of P. Angular velocity of P about A. Angular velocity of P about A is equal Vp over AP. That is, here Vp over AP velocity of P over AP. Now, in triangle AOP, AP equal to AC, which is equal to R cos theta by 2. Angular velocity of C about A equal, that is 2V cos theta by 2 over AP, which is equal 2V cos theta by 2 over 2R cos theta by 2, which gives V by R. Here it is obvious that any point on the wheel rotates about the lowest point at A. This is the lowest point at A, highest point at B here. In lowest point A, which is in the touch of the ground with the same angular velocity. Here at the point A, that with same angular velocity it rotates. Now here notes, the particle A is subject to the following two velocities. We know that linear velocity and linear velocity towards A. The particle A has linear velocity V towards P. V towards P, and tangential velocity, that is V equal omega R towards Q. Here linear velocity towards P and angular velocity towards Q. That means since these two velocities, since velocity towards Q, velocity towards P are equal and opposite and collinear, therefore their resultant is 0. Here these two velocities are equal and opposite. Equal and opposite. That means the point A is momentarily at rest because of the point velocity towards point P and towards point Q are moment equal and opposite. So we can say at momentarily at point A is at rest. Then similarly it can be proved that the particle B, highest point of the wheel, will be subjected to a resultant force 2V and acts perpendicular to OB. That already figure shows. The lowest point A is the instantaneous center of the motion of the wheel. The lowest point of the wheel is the wheel A, that is the point A is the instantaneous center of the wheel, instantaneous center of the motion of the wheel. Center of the motion of the wheel. We have done. Please subscribe our YouTube channel.